Hello, everyone. Welcome back to week 2, day 1 of the Qiskit Global Summer School for Quantum Machine Learning. My name is Bryce Fuller. I'm a quantum computing applications researcher at IBM, and today we'll be discussing quantum support vector machines and quantum feature spaces. So both of the lectures today will dovetail with each other. Lecture 2 will be given by Kristen Teme. So the agenda will go as follows. Part 1 of my lecture will be over reviewing linear classifiers, and in particular, the kernel trick. I know this was discussed at the end of last week, but we're going to go back over it in hopefully more detail. And that will lead us into part 2, which is going to be a discussion of quantum feature maps. So in particular, we're going to be looking at 2 different quantum algorithms for classification of data that use quantum feature maps. One of them is the variational quantum classifier, and the second is the quantum kernel estimator. Once we introduce both of these and discuss some of the relationships between them, we'll be able to, glean some useful insights, and that will lead us into lecture 2 with Kristen telling us about what exactly the quantum feature space is. In other words, what are the features of our quantum feature space, and what are some of the necessary conditions for advantage when using quantum feature maps. Great. So all of the content for this lecture is sort of subsumed by these 2 resources. So if at any point you have additional questions or you want to go back and review the content here in more detail, I highly encourage everybody to go look through Andrew Ng's notes, his lecture notes on support vector machines, as well as the paper Supervised Learning with Quantum Enhanced Feature Spaces, which outlines all of the ideas in part 2, specifically lays the groundwork for what the support vector classifier is, what the quantum kernel estimator is, the relationship between them, and notably the Kristen Teme, who will be giving the next talk after me, is one of the authors on this paper. Great. So part 1, let's get started. I know that linear classifiers have already been covered in this lecture series so far, so we're not going to go through them in excruciating detail, but it's good to make sure that we're all on the same page and have consistent terminology, right? Anyway, so the problem setup is as follows. We assume that we're given a set of labeled data points. In this case, our data points are 2-dimensional, right? And it seems that our labels are colors, right? They're light blue or dark blue, right? In general, it could be any sort of binary label, whether it be dog, cat, but mathematically we'll represent this as a -1 and +1, right? And our objective is that given a set of this labeled data, we would like to come up with a rule that would help us to predict the label of an unseen data point, right? One for which we don't know the data point, that we don't know the label, right? So in particular, consider this gray data point over here as one that we're not really sure which shade of blue it should be, right? And the way that we will do this is by looking for a hyperplane which partitions our data into these 2 sets, right? So for 2-dimensional data, our hyperplane is just going to be a line. So this line, for example, would perfectly separate our 2 data sets, or our data set of 2 classes. However, there's obviously more than one choice here. We could also choose a hyperplane like this, right? And since our decision rule is simply going to be asking which side of our hyperplane our unseen data point falls on, it's kind of obvious that our choice of hyperplane here is important because it will dictate what the label of this new data point is, right? It seems pretty obvious to maybe some of us that it's probably a light blue data point, but we need to formalize this, right? How do we systematically look for the optimal hyperplane? First, we need to rigorously define what we're looking for. So the way that we do this is by defining something called the margin, right? So consider the distance between each of our data points and this hyperplane that we are optimizing, right? What we're going to define the margin as is sort of the minimum distance between any of our data points and this hyperplane, right? you could think of it as sort of this buffer region around our hyperplane. And what we would like is for that buffer region to be very large, which intuitively would sort of correspond to a very confident prediction, right? You can imagine that as we continue to sample data points from this underlying distribution, there's some variance in the where these data points fall on the plane. So if I had chosen one of the hyperplanes that I drew previously, where it came very close to our training data sets, it's conceivable that we might sample a data point later on that will fall on the other side and be misclassified, right? So sort of maximizing this distance corresponds to having very confident correct predictions. Great. So one of the things that I want to draw attention to before we move on from this slide are you can see that some of our data points have been singled out here and labeled in pink, right? So these data points which lie along the margin are important. They're called support vectors, right? And they have a useful interpretation, right? So one thing I want to point out to everybody, and this is going to be really important moving forward to the rest of this talk, right, is that as we've discussed it so far, this hyperplane, or the equation for our optimal hyperplane, is the solution to the problem that we're looking at right now. We want to know how to classify data, and if I tell you the hyperplane, then that answers your question. However, if instead of telling you the hyperplane, I had told you what these support vectors were, I want you to observe that would actually fully constrain your choice of hyperplane, right? In some sense, in a very literal sense, these are two equivalent descriptions of the same solution, right? And this is not just an artifact of the particular data set that I drew on this slide. This is actually a more general feature, right? And so this idea of having dual descriptions of our problem, which look like they're cast in very different forms, is going to be central to understanding what the kernel trick is and to understanding the rest of this talk moving forward. One other thing worth mentioning is feature maps, right? So I know these have been introduced previously. So consider this data set on the left where we have one-dimensional data, right, that is not linearly separable, right? Most of the data that we care about isn't linearly separable. So the idea of using feature maps is simply to assign new features to our data points such that they hopefully are linearly separable after that. So in particular, we're using a feature map here called phi, which is going to take our one-dimensional data and map that into a two-dimensional vector where one of the components is x, the original data point, and the second component is x squared, right? And you can see that in this larger feature space, our data now is linearly separable, right? So you can see I've written the equation for both of these hyperplanes down below. And notably, we've just sort of substituted in phi of x for x over here, right? This is something for the rest of the talk. We will just use phi of x in place of x. It sort of subsumes the case where you don't want to use a feature map because you could just consider it to be sort of a trivial map, right? Great. So our decision rule now will be sort of just to take the sign of this expression, right? Where again, if the sign is positive, it means you're above this hyperplane, or below it if it's negative, right? And this parameter b is simply, you could think of it as the threshold that we're using, right? And so before we go to the next slide and look at the actual equation that we solved to find w, I want to first consider what we're actually looking for here, right? So intuitively, right, we want that each one of our data points is as far away as possible from this hyperplane, right? But not only that, we want to make sure it's on the correct side of the hyperplane as well, right? So you can imagine, casting an optimization problem where you sort of sum over each of your data points and try and maximize the distance between them and the hyperplane, conditioned on them being on the right side of it, right? And if you do that, you end up with an optimization problem that looks like this, right? Where here we are sort of minimizing over our hyperplane, the offset of the hyperplane, and now we have these Lagrange multipliers that we'll be optimizing as well. We have one Lagrange multiplier per data point. So I've highlighted this region in red over here, this term in red, And what this is really doing is just penalizing for each of our data points which fall on the wrong side of our margin, right? So this is very much in line with what we just sort of laid out, right? We're sort of looking at each of our data points in our training set T, and we want to sort of maximize the fraction of them that are correctly classified and are confidently classified correctly, right? However, we want to go ahead and recast this into a different form that will actually be more useful to us. And we can do that by solving these equations down here, right? So in very much the same way that we talked earlier about how you can view the solution to your problem as either the equation of your hyperplane or as being given the labels of your support vectors, we're going to recast this optimization problem into a dual form, very much in the same spirit. And when you do that, it looks something like this, right? I'm not going to go through the full derivation of how you get from this primal problem on top to the dual problem, but I encourage everybody to look through these lecture notes that I've linked below and read for yourself, because it's definitely worth doing. It just goes beyond the scope of what I have time for here, right? But the important thing to note at this time, right, is that this primal problem is a function of W. It's a function of our hyperplane. However, this dual problem has nowhere in it does W appear, right? It seems that somehow this is the same optimization problem in a sense, right? The solutions are the same, yet this one makes no mention of our separating hyperplane. Instead, it just has these inner products between feature vectors down here, right? In some sense, it's asking about the similarity between feature vectors, right? And this is going to be a key observation that is going to allow us to make solving this much more efficient, right? Great. So one of the advantages of using the dual form of this problem, right, is that if I were to be able to calculate these inner products efficiently, that would actually give me all of the information that I need in order to solve this optimization problem, right? Once these inner products are evaluated, the rest of it is more or less trivial, right? It's a convex optimization problem that can be solved using off-the-shelf software, and it can be solved very, very quickly, right? And so you could imagine organizing all of these inner products for your data set into a matrix, which you call the kernel matrix, where the ijth entry of my kernel matrix corresponds to the inner product between the ith and jth feature vector. Of course, this is going to be a symmetric matrix. If you interchange I and j, it's just sort of flipping you're taking the transpose of a scalar essentially. And moreover, it's going to be a positive semi-definite matrix as well, right? And so the key insight here, right, is that these inner products are just scalars, right? And so what this equation is telling us is that we can actually solve for the optimal hyperplane that separates our data in our feature space without ever actually computing any of the feature vectors, right? So in particular, you could imagine a situation where you're using a feature map that gives you many, many features, maybe thousands of features, millions of features even. You could quickly imagine that that is going to be computationally inefficient to solve, right? Just even writing down or computing any one of your feature vectors is going to become prohibitively expensive. But what this tells us is that you never have to do that, assuming you can evaluate the inner products efficiently, right? And it's not directly obvious that that should be easier, but I'll show you an example soon where it turns out to be the case. A very useful example, right? But the insight here, right, is that using that by using this kernel, or people call it a kernel function as well, a kernel matrix, it allows you to work implicitly in very large feature spaces without ever having to represent those feature vectors. Right? And this is a crucial idea that we'll keep coming back to. Right? Great. So over here, I've just sort of written out some notation, right? Sometimes people write the kernel function as being a function of xi and xj, as opposed to just a matrix where you're indexing I and j. That's useful when you write things like this decision rule down here, right? So what this is saying is that if we want to assign a label to some unseen data point s, that in order to do that, all we need is to evaluate the kernel function between s and our support vectors, right? And this is actually another really interesting insight here, is that when you go and you solve this dual form of the optimization problem we have here, what you actually find is that almost all of the Lagrange multipliers, almost all of these alpha i's, are zero. The only ones which aren't zero are the ones that correspond to our support vectors, right? And so this is another way that doing this computation becomes more efficient, right? Is because essentially what this is telling us is that whenever we want to go classify a new data point, all we need to know is how similar it is to the most problematic data points in our feature space, right? In other words, these support vectors are the data points that lie the closest to our decision boundary. And so if you can know how similar your new featured point is for S, right, relative to all of these support vectors, that gives you all of the information that you would need to know in order to classify it, right? This is very much building off of the same sort of intuition that we talked about before, right? That knowing your support vectors is equivalent to knowing the optimal hyperplane. Great. So again, it's not 100% obvious, or it wasn't to me at first, that reorganizing things in this way and writing a kernel function instead of an inner product between two vectors actually buys you anything, right? Is there ever really a case where it's much more efficient to just evaluate the inner product between these two vectors, as opposed to doing it the naive way, where you would have to essentially write down each of these two feature vectors and then compute their inner product? And it turns out that there absolutely is situations like this, and explain one right here. So the radial basis function kernel, also called the RBF kernel or the Gaussian kernel, is written up. This is the equation for it, right? It's essentially telling you the similarity measure between your feature vectors in your feature space, right? And it can be computed efficiently. It takes time that's essentially linear in the dimension of your input data. However, if you were to try and actually go and look at what are the feature vectors that this is actually computing, like what is the feature space in which we are doing classification, it turns out that each of these feature vectors lives in an infinite dimensional space, right? So not only is it more efficient to use the kernel trick, it actually sort of enables you to do things that are not actually possible in principle otherwise, except maybe through some sort of approximations, right? So the RBF kernel is extremely useful in practice, right? But one of the core things that I want to drive home on right here is that moving into large dimensions is a common feature of feature maps, pardon the play on words, but it's not really the whole game, right? It's not the case that the more dimensions you go into, the better off you'll be. The situation is a little more nuanced than that. But it is often the case that we use feature maps that have high dimensional spaces. And by using the kernel trick, it sort of opens the door to be able to efficiently evaluate those models. Whereas before, just feature maps that go into large dimensional spaces were more or less off limits, right? Before we sort of had this insight. Great. So what I want everybody to take away from part one is that if you have a linear classifier that is of this form, right, where your label is assigned based off of the sign of some inner product between two vectors plus b, where one of those vectors is your feature vector, then this statement is true, that if you can evaluate your kernel function efficiently, then we can optimally solve our problem in a very, very efficient manner, right? This is a central insight that we will use later in section 2. Right. Okay, great. All right, so You've had a lot of lectures on machine learning last week and quantum computing. So now let's actually talk about some quantum machine learning, right? So in particular, before we do that, I want to take a brief digression through um, reviewing what it means to measure an observable on a quantum computer. I know this was discussed last week, but I think it's good to refresh on it, and it will be essential to following some of the proofs that I have later in this presentation. So we'll talk about it now. All right, so recall this familiar notation for a quantum circuit where you have sort of a one qubit here where it's running from left to right in time. It starts in the all zero state. And here we're just saying we are going to apply some rotation u. It's not really specific what rotation I'm talking about, but it seems to be parameterized by some parameter theta, right? And so we say that the state of our system at this point is going to be psi, right? Okay. So this you may have seen this symbol of measurement where it's a little box with this gauge inside of it. But I'm going to mean something much more specific when I have this measurement box in addition to some operator inside of there, right? What I mean by that is that I'm measuring this observable h against my state psi, right? And that mathematically corresponds to evaluating this expression down here. Okay, and so this is a very widely used primitive, especially in near-term quantum computing. It comes up in quantum chemistry, optimization, quantum machine learning, and this is often how we sort of think about it. But this is actually a shorthand, and it doesn't really make it clear what is actually happening on the quantum computer whenever you go and try to measure an observable, right? So to be more clear, what's actually happening here is you're preparing your state psi, and then you're performing some change of basis circuit, right? In this case, I'm calling it W, right? And what this is really trying to do is rotate from the eigenbasis of your Hamiltonian, or your observable, into the computational basis, or the diagonal basis, in other words, right? And so, sorry. So the take home from this is that if you can enact this change of basis rotation, and you know information about your eigenvalues of your observable, then you can assign an energy to each of the bit strings that you measure after doing this, after applying W. And so you can essentially take each measurement you get and map that to a number, and then you can take statistics on that and sort of estimate the energy or the expectation value of this observable, right? Now, there's of course more details that I've glazed over here, but the point I want to drive home is that even as I've mentioned it now, there's still a problem with this, right? Namely that if I just sort of pull a random observable out of my hat and ask you to perform the change of basis rotation for that, for one thing, it's not obvious what that change of basis circuit is to you, right? And the other thing is that in general, the length of that change of basis circuit will be exponential if you're going to be considering observables of many qubits, right? So for one thing, it's not clear that it's possible to do this change of basis circuit. And secondly, it's not obvious that you have information about the eigenvalues of your observable either, right? Typically, in a lot of these problems, the eigenvalues of your observable will encode the solution that you're looking for. So if you already knew the eigenvalues ahead of time, it would sort of preclude the need to use lots of quantum algorithms, at least near-term ones. So the solution to this is that we're going to decompose our observable into a sum of much simpler observables, right? So in particular, all observables are Hermitian matrices, and so we can decompose these Hermitian matrices over a matrix basis of Pauli matrices, right? So in particular, I think many of you will be familiar with these. So you have, of course, just the identity. You have Z operator. you have X, and so on, right? And all this is saying is that we're taking tensor products of these Paulis, right? So the nice thing is that we know that we can always decompose an observable as a weighted sum of these Pauli operators. And moreover, the Pauli operators are very well behaved whenever we want to take expectation values of them. If we want to measure the expectation value of a Pauli operator, it's usually very straightforward to do. The change of basis circuits are known ahead of time, and the eigenvalues are known ahead of time, and it's easy to compute these quantities in here. So if we want to measure h, what we really end up doing is decomposing it as a sum of things that we know how to measure. We measure those smaller pieces, and then we sum them back up to get our estimate of h, right? And there's plenty to be said about this process and the shortcomings of it, and optimizing it to make it more efficient. But the thing that I want you to take home from this is that you can decompose observables in the Pauli basis, right? You can decompose any Hermitian matrices in the Pauli basis. And this is going to become useful to us later on whenever we are doing some proofs. Okay, great. So what is a quantum feature map? Well, I think it's more useful to answer this question by first trying to define, what does it mean to classify data on a quantum computer, at least in the near term, right? And I think we'll sort of naturally arrive at an answer to this question pretty soon. So first, I want to discuss what's called the variational quantum classifier. So these sort of variational circuits, or sometimes they're called parameterized quantum circuits, they're ubiquitous in near-term quantum computing. It's the bread and butter, right? And so I've drawn one over here on the right. It's just some single qubit rotations. There's 2 qubit interactions. All of them are parameterized by these theta angles, which are not yet specified, right? So if we're going to build a quantum classifier out of this, there's a couple things that we require. So in particular, we need a way to feed our data into the circuit, which seems pretty natural. And we need a way to extract a label from the circuit, ideally a plus one minus one label, right? So in order to do this, think what's like the first idea that comes to your head, right? So for me, I would say, why not just feed our data into some of these gates, right? So I've just sort of relabeled all of these parameters so that the thetas start later on, and we're going to say that all of these single qubit rotations here are going to be parameterized by our data. In this case, assume that our data is 4-dimensional and real. Right? So, okay, great. That solves our first requirement. Second requirement is we can just measure a Pauli observable to assign our label. We know that the eigenvalues of the Pauli matrices are always plus or minus 1. So if we measure the expectation value of one of these operators, then it's always going to be between plus and minus 1. And so that seems like a pretty useful thing there. And then we can just round that answer or threshold it on 0 or some other value. So that seems great. And then with the rest of the circuit, we can just optimize these remaining parameters to improve performance, right? So, we've given a way to input data and a way to get a label. There's no reason to believe that the label it gives us will be useful yet. So let's just say we're going to optimize these thetas and try to make this classifier be as useful as possible, right? So this is the setup, right? It's sort of the most natural, obvious thing you might try first, right? So I'm just going to sort of black box each of these subcircuits, take away some of the complexity of them, right? So I'm going to call this first subcircuit phi of x and the second subcircuit w of theta, right? And when we go and measure this Pauli observable, we're of course going to get a number between -1 and 1, and the equation for that is written down here, right? So once that gives us a value, we can then, once that gives us a value, we can then choose a threshold b, and our decision rule will simply be that if the value we get is greater than b, we call it +1, and if it's not, we call it -1. All of this seems pretty sensible. So I'm just going to get rid of some of the writing, make some space. We know that, of course, this decision rule is equivalent to saying that we're just going to take the sign of this expression here. So now we're sort of in a position to answer the question we posed at the beginning of part 2, right? Namely, what is the quantum feature map? So in this case, it's just a circuit. It's just some subcircuit, right? In our particular example, it's just a single layer of 1-qubit rotations, right? Okay, so what exactly is W doing? It's not 100% clear yet, but one thing I want to point out is that when we were discussing how you measure an observable, right? We had this change of basis circuit W, right? And it's no coincidence that I use the same letter for this, right? So what I want to point out is that you can think of the action of W as sort of parameterizing your change of basis circuit here, right? So in particular, you could imagine rewriting this block right here as sort of h of theta, where I've sort of drawn parentheses around this and simplified, right? So in some sense, you can think of what W is doing as sort of optimizing over the Hamiltonian, or optimizing over the observable that you're going to measure against your feature vector. It's okay, that seems reasonable. Now, it's not immediately obvious, or at least it wasn't to me when I first saw this, whether you would expect to get an advantage from this, right? Is W doing something that is, fundamentally quantum? Is this apples to oranges from what's happening in the classical case? Is it it's not really obvious what's happening here. But the claim that I'm going to make, and that we're going to prove shortly, is that this model is just a linear classifier. That this is doing exactly the same thing that we talked about in part 1. And it's not immediately clear why that's the case, but we're going to step through the proof and observe that it is in fact the case. Okay, great. So I'm going to try and take this one step at a time and explain what I'm doing at each point. I realize that some people that are following along may not be terribly familiar with proofs, and so we'll try to make this really accessible and easy to follow, right? So first, we're going to apply the observation we had before, that we can just sort of rewrite this W theta Z W theta as H theta, right? We're just saying that we've sort of absorbed those rotation circuits into our observable, and we're saying that this is now some new observable which is parameterized. So, okay, great. Next thing to observe is that this expectation value here is a scalar. It's a single number, right? In other words, it's a 1-by-1 matrix. So you can always take the trace of a 1-by-1 matrix. It's just going to be equal to itself. And so let's go ahead and do that, right? Again, these are nothing really profound has happened here. But the nice thing about throwing the trace around the outside is that we can take advantage of some of the properties that it has, right? So in particular, if you're taking the trace of AB, and A and B satisfy certain properties related to their dimensions matching up, then you can sort of reshuffle things around inside of the trace, right? And so in particular, we're going to sort of move one of these feature vectors over, so we have a bra and a ket sort of pushed up against each other, right? And this may seem familiar to some of you, right? Because this is just a density matrix, right? It's another description of our state, similar to a state vector, but it captures some slightly different information, right? So let's just give that a name, right? We'll say that phi of x, no bras or kets, is this density matrix, right? I'm going to say it lives in sort of this complex vector space of size 2 to the n by 2 to the n. So, okay, great. Okay, and so if you plug that back in, we now have this expression down here for what f of x is. It's the trace of h theta times phi of x. Okay, so the next step is we basically just want to rewrite each of these two quantities, right? And we're going to do it in a common basis, right? So recall from the beginning of part 2, when we were discussing how you can decompose an observable as a sum of Paulis, we're going to do exactly the same thing here, right? Where we are going to decompose this in the basis of Pauli matrices, right? So, you know, similar to how you would do this for any other vector, you have the inner product between the vector you're decomposing and each of the basis states times the basis state, right? So in this particular case, this inner product is going to be the Hilbert-Schmidt inner product. So I'll just go ahead and replace this inner product with the corresponding quantity, right? This is how the Hilbert-Schmidt inner product is defined, right? And the other thing I want to point out is that density matrices are also Hermitian, right? So we can basically do the exact same thing for phi of x as we're doing for h of theta, right? So this is the same equation. I've just sort of swapped in phi of x. So okay, this is great. So again, these trace of h theta and Pauli alpha, Pauli sub alpha, this is a scalar. So I'm going to go ahead and just relabel this, right? We'll define these quantities to be the scalars, these coefficients that are going to go on each of our Paulis, and they're indexed by this parameter alpha. Okay, great. So if you substitute that in, you get something like this. So again, nothing crazy has happened so far. We're literally just rewriting things and reorganizing terms. So, all right. So if we go back to our equation for our estimate that we're getting out of our quantum computer, we can plug in these decompositions, right? So we've just basically decomposed each of these quantities in a common basis, a Pauli basis. And then from here you can just simplify. So pull the normalization out front, combine these into one sum. So notice that now one of the alphas is now a beta because we can't reuse indices in one expression like this. And observe also that the trace operation is linear, so we can actually distribute it inside of this sum. So we'll go ahead and do that, right? Now, this is particularly useful to us because the Pauli matrices have some very useful properties at this point, right? In particular, we know that the trace of two Pauli matrices is either going to be, or the product of two Pauli matrices, excuse me. Sorry, this shouldn't be a comma here. The trace of the product of two Pauli matrices is always going to be either 2 to the n or 0. And there's a really intuitive reason for this, right? Which is that all of the Pauli matrices have trace 0 except for the identity, right? It's the only one of them that has non-zero trace. And we also know that every Pauli matrix or every Pauli observable squares to the identity, right? So what that tells you is that if A is not equal to B, then you will get some other Pauli observable, which is not the identity. And that if A is B, you will always get the identity. And therefore, your trace will be 2 to the n. So the reason this is very useful is it allows us to eliminate one of these indices. We can go back down to just alpha, right? And again, the reason for that is because any of the terms in this sum where alpha and beta are not equal will be multiplied by a 0 coefficient. So we can just exclude them. Okay, great. So from here, it's starting to become more clear why this is a linear classifier. If you look, we've reorganized things. We now have this is starting to look eerily similar to an inner product between two vectors, right? You have some vector h sub alpha and some vector phi of x, or sorry, h of theta and phi of x, and they're summing along one common index, right? Very much in the same way you would compute an inner product between two vectors, right? So we know this gives us a value between -1 and 1, and once again we can just pick a threshold b, and we say that the label is the sign of this expression, and it's very clear that that this is a linear classifier, although it's not yet clear what space it is doing that we are classifying in, right? So what exactly these alpha A of x's are hasn't really been explained, and that'll be the subject of Kristen's lecture, or at least part of it, right? But the point that I want to drive home is that, when we were on this similar slide earlier, we said, what exactly is W of theta doing, right? Well, we said that W of theta is optimizing over our choice of Hamiltonian, right? But it's actually doing more than that, right? So now that we know that this variational quantum classifier is a linear classifier, W theta is actually parameterizing our set of hyperplanes that we can pick from. And this is kind of a problem, actually, because you'll recall also that we mentioned that if you wanted to measure an arbitrary observable, the change of basis circuit which executes that is going to be exponentially long in practice, right? And we know that we didn't pick an exponentially long W of theta. I mean, we just had a relatively short circuit. So it must be the case that there are Hamiltonians, or excuse me, there are observables that we could measure, in other words, hyperplanes out there that are not accessible by W sub theta. Right? It's sort of parameterizing a subset, a very small subset of the total possible hyperplanes. So let's write that. So right about this time, it starts to become relevant, the take-home message from part 1, right? Which is essentially that we've observed that what this is doing is actually just a linear classifier. It is of the form that we mentioned before, right? And so we're using W to try and learn an optimal separating hyperplane. And training W is expensive and it's costly and not guaranteed to even find the optimal solution, even of the subset that it has access to. And what's more is that it's very possible that the optimal separating hyperplane is not even reachable by W sub theta, right? But again, we know that if only we could compute the kernel entries, if we could compute the kernel function for this feature map, then we could solve this problem efficiently, right? That was the conclusion from part 1, that if you were able to efficiently compute the overlaps between feature vectors, then this problem can be solved optimally and it can be solved efficiently, right? And so what we're going to show next is that it actually is the case that you can compute these overlaps, and that is the next model that we're going to talk about. The quantum kernel estimator, sort of, you can think of it as the analog of the variational quantum classifier. However, we're going to now skip this process of sort of optimizing a costly PQE circuit, parameterized quantum circuit. And instead, we're just going to directly evaluate these kernel entries so we can solve the dual form of the problem more efficiently. So this is the circuit which you use to compute a specific entry, and let's take it one step at a time and see what it's doing. Right. So if we look at the state of the algorithm at this point, after we've applied our first feature map, but not this second part of the circuit, we say that the state of our system, sort of in the state, we start in the 0 state, we've applied phi of xi. Okay. Then as we apply now the inverse of our feature map for a different data point. And so we've prepared our feature map for one data point. We're now going to uncompute the feature map for a different data point. I'm going to now do this part in red. It's going to correspond to applying this operation. inverse of phi of xj. Great. Now, if you look at the state that we have here, and you ask, what is the probability that after preparing the state and go and measure just like normal, what is the probability we measure the all zero string, right? Measure zero state. Well, to compute that, you would just sandwich a bra 0 over here and take the norm squared, right? And if you do a little bit of simplification, it's easy to see that what we're actually computing here is sort of this following quantity. Which is exactly the entry of the kernel matrix at ij. Great. So we can use circuits of this sort to additively estimate entries of our kernel matrix. Okay. So I'll go ahead and move that over here, make a little bit of room for ourselves. And now I want to go ahead and just write out the full end-to-end algorithm of the quantum kernel estimator and all the things that we're going to be doing now, just to be clear, right? So we're going to iterate over our training set T. So for every I in J in our training set, we're going to do the following. First, prepare this particular state, which is just the sort of applying our feature map for one data point and applying the inverse of the feature map for another data point. Notably, this can be symmetric. It doesn't have to be the ordering of which I and J we pick doesn't matter. If you flip xi and xj, you get the same thing. Okay. And from here, we're going to measure the probability, take statistics on how often we measure the all zero string after doing this. And we're going to let that equal our kij, our kernel entry there. And we're going to do this for every I and j. So we're going to fully evaluate all the elements of this kernel matrix. So if we have capital N data points, this is going to require the capital N squared different circuits. And then we're taking multiple shots for each of those circuits to get an additive estimate of our entry. Once we have that estimate of K, our kernel matrix, we're going to just plug that directly into the dual form of our problem, right? This is, as we said before, once you've evaluated these kernel entries, the rest is a convex optimization problem that can be solved efficiently with off-the-shelf software. Great, and recall that the actual solution that we get back when we do this will be a set of Lagrange multipliers, right? So these are just going to be scalars, one for each of our training data points. And they're going to essentially tell us which of our data points is actually a support vector. Right? And recall, this is an equivalent description of our hyperplane. I can either tell you the equation of our hyperplane, but unfortunately it's going to require exponentially many coordinates. So it's an exponentially long list of numbers at this point. Or I could tell you what my support vectors are. And so that's what this was going to do. Okay. So to sort of tie all this together, our final classification rule, when we want to assign a label, will be given by this function. It's very familiar. It's just the sign of our kernel matrix, our kernel function between our support vectors and this new unseen data point S, weighted by our Lagrange multipliers. And then of course we have this offset B, which is just determining, do we threshold at 0 or do we threshold at some other value to determine if it's our actual label. Great. So with that, I want to sort of discuss a few takeaways that I hope everybody leaves this discussion with, right? So I've abused a little bit of set notation here, but one thing to note is that the quantum kernel estimator is a strictly more powerful algorithm for the tasks we sort of outlined than the variational quantum classifier, right? And I think the line that you should sort of internalize is that what the quantum kernel estimator is effectively doing, right, is it is optimally solving a variational quantum classifier model with an infinite depth W theta, right? So in order to do that in general, right, you would need a infinite depth W theta and you would need to optimize it presumably for infinite time, which is just something that very hard to compete with right? And moreover, right, one thing that I hope is clear is that if you're hoping to get any sort of advantage by using the quantum kernel estimator or either of these techniques, really, you need to take care that phi of x is hard to classically compute, right? So in particular, for the example that we chose, we just used a feature map which was a single layer of 1 qubit rotations, right? And the thing to note is that that circuit generates no entanglement, and so this final circuit that we use to estimate our kernel entry is going to be very, very easy to simulate classically. And so there is no chance that you would get any sort of advantage from doing this, right? Now, this is going to be a sort of necessary but not sufficient condition for quantum advantage, that we are going to need phi of x to be hard to classically compute. However, that's not necessarily the whole story, right? It's not the case that just if you find some hard to compute function that it gives you a good kernel. And so in the next talk, Kristen's going to go into a little bit more detail on what some of the other conditions are for necessary conditions for advantage and how you might want to go about thinking of designing a quantum kernel. So I think that sets us up nicely to go into his talk, and